No. Thanks for asking.
I've seen you, I did one once. Real brown leather jacket. Yeah, it just looks like a rain jacket. Yes, it's probably better. But I'm
Hello everyone. So I hope you have a good week. The first thing I want to talk about is after thinking about that, for the homework, I think I'll set back to the deadline on the Tuesday rather than a Friday. So I'll give you a week to do. So when I post homework on Tuesday, so you have a lecture on Friday, right? So I would say maybe 50% of the homework that you can do before the lecture, and then for the rest of it, so after the Friday lecture, so you can do it, okay? The reason is if it's on Fridays, then there will be a lag between I can talk about your homework and the current progress, okay? So the lag will be 2 weeks rather than 1 week, okay? So for this, I'll change back to Tuesday next week. So for this week homework, so I have posted on Tuesday. So the deadline will be on next Tuesday, the coming Tuesday, okay? So I'll change it back to Tuesday, 12 p.m., okay? So that next week I can talk about week 2 homework already, when we are having a class, and also your GTA Kaizen having a class on Thursday. So we can talk about your homework after just 1 week, okay, rather than we need to wait for 2 weeks if you submit it on Friday, okay? So I will change it back to Tuesday here. That's the first important thing, okay?
So just to double check, so week 2 is due next Tuesday?
Yes,
Okay.
yes. So week 3 I'll post on Tuesday, and then it will be due on week 4 Tuesday, and so on and so forth, okay? I'll change it back, okay? So this Friday will be changed to Tuesday. So we reduce the lag. The second thing is, so if it's still not clear to you, so you have the lecture notes can be downloaded here, so you should all have done that. And the handwritten notes, so you can see that if you click in it, I have already uploaded the last week scanned lecture. So if you have a look, so I've scanned all of these. So every week I'll do that. I'll do that over a weekend, okay? So there really is no need to try to write down everything, but as I said, listening will be more important. And so our GTA has very kindly uploaded some slides, so you can have a look, okay? So also review of what we have been talking about. Now, there's also lecture recording, so if you are not, so if you click in, so I suppose not many of you have done that, so you can see that all the lecture slots have been arranged. The first lecture is already there, so if it's black here in this square, so it means the lecture is still not there, but it's now being recorded, this lecture. So if you click, you can see all the list of lectures, okay? So click the one that you want to revise on. That's the second thing. So exercise 2, so will be the coming Tuesday will be the deadline. So I will provide an upload link later on after today. Okay, so that's all I want to talk about. So if you get any questions, so let me know, okay? About the lecture itself, the content itself, or any administrative things, so let me know. So let's go back to what we had done last time. So let's see. So remember last time we talked about the strong stationarity and the link between weak stationarity and Gaussian process, right? So you need to remember the definition of what a Gaussian process is, and how do we show that in fact Gaussian process, when combined with weak stationarity, it goes back to strong stationarity, okay? So if strong stationarity you think it's too strong of an assumption, so best you don't combine that with assuming normality for your model as well as weak stationarity, okay? So most of the time people will use weak stationarity, so that means you shouldn't really use assuming normality for your model distribution, basically, which is in econometrics, so people used to do this. Nowadays people are getting better away from assuming normality. Okay, So let's get back on track to what we will continue today. So in a nutshell, so we will talk about some basic time series models as promised last time. So after talking about the purpose of stationarity and the two kinds of stationarity, so you have seen. And after that, so we will talk about some useful measure to look at, and we will look at some data examples as well in the lecture note. Okay, so let's start with talking about the easiest stationary time series. That is fundamental to the study of time series itself is the white noise. So let's define what is a white noise first. So if xt is such that, so firstly, so you have the mean mu, which is equals to the expectation of xt. Okay, so every xt has the mean, which is a constant, and it's also finite. So that's the first condition. So similar to weak stationarity. Now, how about the second order moment? So covariance of xt and xt plus h. This time not only finite, but it's zero, okay, for any lag h which is not zero. So covariance of any pair of xt's in your time series is zero. Now how about the variance? Well, the variance is satisfying the condition in weak stationarity, which is constant and finite. Okay. So this is white noise, okay? Then we say xt follow the white noise, and our notation in this course, and in many other textbooks as well, the notation is this, so Wn with a finite mean mu and variance sigma square, okay? So Wn is not really normality, okay? It's just white noise, okay? So Wn is the abbreviation for white noise. And the mean mu and variance sigma square is the time-independent mean and variance. So the easiest example you can play with is, of course, xt, let's say, is IID. This time really is normal, IID normal mean mu with variance sigma square. Then, of course, this is a white noise as well. Why? Because, well, the mean is constant, time independent, satisfying condition 1. How about condition 2? Well, it's IID, that means all the covariances are zero because all the xt's are actually independent, okay? Then, of course, the covariance between any pair is zero. So xt is an obvious white noise, so we say it's IID white noise, okay? Or any IID distribution, basically, where if it's a uniform AB, then of course it's also a white noise, but the mean, of course, you need to calculate, so that's A plus B over 2, and the variance, I forgot, okay, whatever. So mean and variance, when you are abbreviating it as a white noise, so you need to know at least the mean and variance, okay? So why white noise is important? Well, why is it called white noise? Well, it is out of scope of this course. It used to be inside the scope of the time series course that you have seen in the last part of the Moodle page. Okay, so it's related to the topic called spectral frequency domain analysis of time series, but in this course, so I removed that and focus more on a little bit more multivariate time series, which is To a very, very large extent, I think it's more useful to majority of students. But frequency domain is also another big topic for time series analysis, but I'll remove that. So white noise is basically related to frequency domain. Okay, so if you're interested in that, you can come to me and let me know. Okay, why is it called white noise? Why is it not called pink noise, brown noise, whatever? But okay, let's focus back on after white noise. So we're basically constructing simple time series so that it may be approximately useful for real data. Okay. Now, white noise obviously is very fundamental, but most of the time series you see usually is not white noise, right? So let's construct a little bit more complex time series from white noise. So a little bit more complex will be the moving average process. So what is the moving average? Well, as the name suggests, if xt is defined like this, okay? So it's defined as your xt equals to a constant alpha plus kind of a linear combination of these epsilons, okay? So theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 up to theta q epsilon t minus q, where your epsilon t now follows a white noise with mean 0 and variance sigma square, okay? And your theta q here is not 0 to really define the order of this MAQ process, okay? So if theta q is 0, then it's not really MAQ, but MAQ minus 1 at most, right? So we define theta q to be not 0 to identify the order of this moving average process. And the abbreviation is, we say xt follows an MAQ process. So here, this curly sign here is not distributed as, but it's basically just following an MAQ process, okay? So it's kind of an average of the epsilon t's back to epsilon t minus q, okay? If all the thetas are equals to 1, then it's exactly a kind of average, right? It's sum of them, okay? And with this theta 1 up to theta q, so it's basically a weighted average of the epsilon t's from epsilon t minus q up to epsilon t, okay? And why is it moving? Because as time t goes from 1 to 2 to 3, as time t moves, then this average also moves, okay? The range of this average also moves. Therefore, it's called moving average. And I give you a very simple example. So let's say xt equals to epsilon t plus theta epsilon t minus 1. So this is an MA1 process for theta not equal to 0. If epsilon t is a white noise, okay? So epsilon t has to be a white noise. So it's an MA1 process. If epsilon t itself is some other process, then you need to analyze further what xt exactly is. Okay, but if epsilon t is a white noise and it's basically it's a linear combination for the xt's of then xt follows an MA process. Okay. Any questions so far? Yes.
Yes, with white noise, is it like normally distributed, or because you can have a uniform with zero mean and like
Yeah. You don't need to. You don't know about the distribution. Okay. So here we haven't specified it. The only thing we know is so it has a finite mean and finite variance, which is time independent, and it's specified there. But it can have different distribution. Okay. Yeah. Okay. So let's move to another kind of process before I let you look at some examples. So another process which is also important in your subsequent study is the autoregressive process. So what is autoregressive? So if xt is has the following definition, okay, so if xt again has a constant alpha, now but this time instead of the sum of the epsilon t's is the sum of the xt's, okay? Not any of them, but the path p of them, okay? xt minus 1, xt minus 2, back to xt minus p. And it's a kind of a average of them, and weighted average. Epsilon t again is a white noise, okay? With mean 0 and variance sigma square. Again, your phi p here is not 0. To really define the order of this autoregressive process. And then the abbreviation is xt follows now an AR model, autoregressive process of order p. Okay? So why is it called autoregressive? Well, it's really like a regression model. So xt regress on some covariates, but these covariates is none other than the some variables from the same time series. Okay, from the past. For the past of your time series, if your current time is time t, then you regress this on some past values of the xt's. Okay, xt minus 1, xt minus 2. If it goes back to xt minus p, then this is an autoregressive process of order p. Okay. So if you have xt equals to, let's say phi xt minus 1 plus epsilon t, then as an epsilon t follows a white noise with mean 0 and variance sigma square, then we say xt follows an AR1 process. If phi is not 0, of course. So it's very simple. Moving average and autoregressive process. So you have exercise on these kind of processes. But let me give you some examples first. Okay. So these examples. Sorry about that. Is it still copying? Okay.
Excuse me.
Yeah.
What is phi supposed to be in this example? Is it a function or a...
Oh, it's just a coefficient. It's just a constant. Sorry about that. Okay, so this is, and phi is not 0 in this example, so it's an AR1 model, but it's a constant.
Is that the same with theta in the previous model as well?
Yeah, they are all constants.
And in this example, why don't we have this constant parameter alpha?
Because it's just represent a mean level, basically.
Okay.
It's not exactly the mean, but it represents the mean may not be 0. Okay. In fact, we will calculate the mean very soon. Okay. If we assume the process is stationary. Okay. Okay. Now this time, let's look at the xt equals to a certain MA1 process. So xt follows an MA1 here. For theta is not 0. Okay. The first question you should ask is xt stationary? When I talk about stationary, it means weakly stationary, okay? So unless I specify strong stationarity, strict stationarity, any stationarity you see will mean weak stationarity, okay? So is xt stationary? So is it weakly stationary? Well, you can check. So by first principle means you go back to definition of weak stationarity. So what is the definition of weak stationarity? Well, you look at the mean, right? You look at the mean of xt. Well, with this process, the mean is, well, alpha. Just alpha, right? Alpha plus expectation of epsilon t plus theta times the expectation of epsilon t minus 1. They are all 0, right? All equals to 0, so this is just alpha. And alpha, of course, is a constant, time independent, and also finite. Well, that satisfies the first condition of weak stationarity. How about the second order moment? For second order moment, you usually need to check two things. First of all is the variance. What is the variance of xt? Now, the epsilon t swallows a white noise. Alpha is a constant, so variance of xt is the variance of just a random variable. Alpha is a constant, so variance of it, well, you don't need to include that, okay? But what is the variance of the sum of these two things? First of all, they are uncorrelated, okay? If it's correlated, then you remember variance of x plus y is variance of x plus variance of y plus 2 times covariance of x and y, right? That's very basic statistic. Here, covariance of epsilon t and theta epsilon t minus 1 is 0 because it's a white noise. So it's just the variance of epsilon t plus the variance of theta epsilon t minus 1, theta taken out, becomes theta squared, the variance of epsilon t minus 1. This is what? Well, both are sigma square, okay? So it's 1 plus theta square times sigma square. So what are we doing? Why are we calculating the variance? Well, this is, first of all, constant, which is finite and time independent, okay? So that's a good start. Finally, let's look at for h larger than 0. So for some lag larger than 0, what do we look at? We look at the covariance between xt and xt plus h. For MA1 model, so there's no simplification, so we just expand all of them. So first of all, xt equals to alpha plus epsilon t plus theta epsilon t minus 1. Don't write down the alpha. We're talking about variance or covariance, or all the constants, you can ignore them. And the next t plus h, ignoring the alpha, there's epsilon t plus h plus theta, epsilon t plus h minus 1. And how do we expand this? How do we expand this? So covariance of the sum of two random variables with another sum of two random variables, right? So you basically kind of expand it like multiplying polynomials of two terms. So it will be the covariance of epsilon t, first of all, with epsilon t plus h. So it's basically these two terms, right? And then plus covariance of epsilon t and theta, epsilon t plus h minus 1. Theta can be taken out. Epsilon t plus h minus 1. So it's basically these two terms. And then plus, now how about the original theta epsilon t minus 1? So theta taken out first. Covariance of epsilon t minus 1 and epsilon t plus h. So it's these two terms, right? And then finally plus covariance between theta epsilon t minus 1 and theta epsilon t plus h minus 1. Both theta can be taken out to become theta squared. And the covariance between epsilon t minus 1 and epsilon t plus h minus 1. So it's these two terms now, finally. Okay. So it's basically 2 by 2, it becomes 4 terms, right? Can we simplify this? Well, we assume the lag h is larger than 0 here. And remember, epsilon t is a white noise. So what does it mean? Any covariance between epsilon t's with different time points, they are all 0. So is this 0? Well, this of course is 0. Okay, h is larger than 0. Epsilon t and t plus h, of course, they are different time points. So this is 0. Okay. And how about this? Well, t minus 1 and t plus h, well, h is larger than 0, so this definitely is 0. Okay? So does the last term, t minus 1 and epsilon t plus h minus 1, h is larger than 0, so they are different time points. So all of these are 0, okay? So sometimes I'll use this notation to mark that they are all 0, okay? So what you're left with is the second term here. Theta times covariance between epsilon t and epsilon t plus h minus 1. So you ask, why is it not 0? If h is 2, then certainly it's 0. H is 3, certainly 0, but not when h equals to 1, right? When h is 1, then this is sigma square. So it's theta sigma square when h is 1. And 0 when h is larger than 1, okay? So we spent some time on it, so what's the original purpose of what we are doing? So we are asking, is xt stationary, okay? So are we done here? Have we proved stationarity? Well, stationarity, remember, needs the covariances. It's a function of lag h. And in that definition, lag h can be negative. In this calculation, well, you only assume h is positive. If you don't assume h is positive, well, this thing cannot, first of all, be calculated. So it would be too complicated, okay? So that's why we assume h is larger than 0. So the remaining thing to do is to consider h is less than 0. But do we need to repeat this calculation? Well, the answer is you don't, okay? So we don't repeat the above calculation at all. So let's look at this. So we have proved that covariance of xt and xt plus h is time independent. That's the key, when h is larger than 0. So covariance of xt and xt plus h. Okay, I know h is less than 0 now. So let's write it in reverse order, xt plus h and xt. Now t plus h here is a time point less than t because h is less than 0, okay? And immediately, so we actually know what is the value of this. What's the value of this? To make it clearer, so if we define t plus h as, let's say, t prime, then this is xt prime plus absolute value of h, right? Where t prime is t minus absolute value of h. We define this as. Why do we need to do this? Well, because I don't want to repeat the above calculation. Look, the above calculation for h is larger than 0. For any time t, I've calculated the value here. Here, my time t becomes t prime, and my h is absolute value of h. So this is theta sigma square, when this absolute value of h is larger than 1 and 0. This is equals to 1, sorry. When this absolute value of h is larger than 1, okay? When it's 1, it's theta sigma square. When larger than 1, is 0. We have calculated that, okay? So, in summary, when you are trying to show that something is stationary and you're considering positive lag, and you have done the calculation, okay, for positive lag, it really is time independent and is a function of the lag h, then you don't need to explicitly consider h less than 0 anymore because of this, okay? You see, this argument, these two lines here are generic, okay? So if for positive h, covariance is indeed just a function of h and time independent, then it automatically translates to when h is less than 0 because of this argument here in these two lines. Okay? So
Basically, we just shift the time series.
yes, we just shift the time point, okay? Just shift it by absolute value of h here. So you don't need to recalculate everything when h is less than 0, okay? And so from here on, I will assume that you know this trick, okay? So you can just say, well, so when h is less than 0, it's similar, okay? But when you write this similarly, it means that you understand that you have calculated for h larger than 0, it really is time independent and just a function of a lag h, okay? If this is the case, then this argument is valid, okay? So when h less than 0, no need to explicitly do all these proof anymore. So therefore, indeed, covariance of xt and xt plus h, no matter what h is, we can calculate. And first of all, when h is 0, we have calculated it. This is the variance. And it's theta sigma square when h is plus or minus 1. So plus 1 or minus 1, they follow the same calculation. but everything else is 0, okay? So you can write O/W, it means otherwise, okay? So 0 otherwise. And by the way, so we have done the ACVS for MA1. So this is stationary. It's weakly stationary because variance and mean, they are time independent, they are finite. Covariance is a function of h, but time independent. And all the values are finite as well. So by definition, this is indeed a weakly stationary process. And in fact, any MAQ process is weakly stationary. And the ACF, so last lecture, so we have talked about what ACF is. It's just a normalized version of ACVS. So the ACF or ACVS has a cutoff at lag Q. So what do I mean by that? So first of all, any MA1 process, so you have proved that it's stationary. And if you look at the ACVS, so since we have proved it's stationary, so of course this represents the ACVS, the autocovariance sequence. What's the property of this autocovariance sequence for this MA1 process? Well, Q equals 1 here, and when lag H goes larger than 1, go beyond 1, all the covariances are 0. So we say MA1 has ACVS cutoff at lag 1. Cutoff at lag 1 means beyond 1, all the covariances are 0. And for MAQ process, there's also a cutoff, but cutoff at lag Q. Okay? So this is something you can prove is a little bit tedious, well, and so it won't be asked in very time-tight exam, okay? So, but you need to remember how to prove, let's say, an MA1 process is stationary and also has a cutoff at lag 1 for the ACVS, okay? And remember the general rule, so MAQ has a cutoff at lag Q for the ACVS, all right? Any questions?
Would there be a way to prove that it's strongly stationary?
In general, it's not strongly stationary. Yeah. So, of course, it depends on your epsilon t's. Okay. So, if in the end it's a Gaussian process, then it can be strongly stationary. But in general, it's not. Remember, the white noise can be something other than IID normal. Okay. So later on, when we do financial time series, when we do arch and gouge model, so you see a perfect example of that. Okay. All right. So let me get you some more calculation before I show you something on screen. Okay, so this is page 5. Let me know if you have any questions, okay? So, 6. So I'll give you another example. So we have seen the MA1 process. So let's look at the AR process. Okay, so let's look at the AR1, where your epsilon t here is a white noise. with mean 0 and variance sigma square again. So here we are doing things a little bit differently. Let's assume xt is stationary. So you ask, how do we actually prove this process is stationary? Well, the answer is it may not be stationary, but under certain condition, it's stationary. And later on, you'll see a very simple theorem that teach you how to see very quickly if a process is stationary or not. Okay. For now, assume this AR1 process is stationary. Okay. So the purpose is, so I want to show you some calculation involving finding this autocovariance sequence of this process. Now, this is stationary, so the ACVS exists. So let's SH be the ACVS. The first of all, expectation of xt. Okay, so this is, now this time of course alpha has to be here. In fact, it plays a very important role in the mean. So alpha plus phi times expectation of xt minus 1. That's it, right? We take expectation on both sides of this model. That's the result. And coupled with stationarity, let's say if mu is the expectation of xt, then this equation means what? It means mu equals to alpha plus phi times, what is the expectation of xt minus 1? Well, it's stationary, we assume that. We assume it's mu already, so it's mu. So therefore, if you solve for mean mu, this is alpha divided by 1 minus phi. If your phi is not equals to 1, of course. In fact, if phi equals to 1, you can prove that the process is not really stationary. Okay? How about the variances, covariances? How about the ACVS? Okay? So, for these kind of processes, so you see the questions in the exercise if you have seen them earlier. So I have several questions on finding these ACVS, okay? So there's some, not tricks, but some usual way to calculate it. So the first one, people usually can take variance on both sides of a model. So if you take variance on both sides, the left-hand side is variance of xt. Variance of xt under our notation is S0. Remember, SH is our ACVS. So variance of xt is S0, like 0. It equals to what? Variance of alpha, so you can ignore the alpha. So taking variance of phi xt minus 1 plus epsilon t. This is what? Just expand this time. So phi taken out, phi squared, or variance of xt minus 1. And then plus variance of epsilon t. And don't forget the covariance of the two terms. So taken phi out, so 2 times phi times the covariance, sorry. So it's the covariance of xt minus 1 and epsilon t. And this term here, later on, we'll see that if this model is stationary, this is in fact 0. So in fact, covariance of xs and epsilon t is 0 for s less than t. If xt follow an AR model, follow a stationary AR model. Okay. So here you follow the stationary AR1 model. So this covariance of xt minus 1 and epsilon t, so t minus 1 is less than t, so it's equal to 0. So later on, we will see that this is true, okay, with a indication of this. But for now, let's take this, remember this, and this will be the case then. Phi square, variance of xt minus 1, that's S naught as well. And then plus variance of epsilon t, that's sigma square. Right? So therefore, your S naught can really be calculated in terms of the parameters of the model. So first, sigma square divided by 1 minus phi square. And this is, of course, can only be finite if phi is not 1. In fact, if phi is less than 1 in magnitude. Well, you can say, well, when phi is larger than 1, it's still finite, but the problem is when phi is larger than 1, this is a negative value, right? And what are we calculating here? S naught is a variance of the process. Variance cannot be negative, right? So when phi is larger than or equal to 1, so, well, it's not a proof, but it kind of indicates that it may not be stationary. In fact, indeed, when phi is larger than 1 in magnitude, it cannot be stationary. Larger than or equal to 1. This AR1 process cannot be stationary, okay? It can only be stationary with phi if phi is less than 1 in magnitude. Okay? So that's S naught. Well, how about the SH? For H different from 0. We're calculating the ACVS here. Well, remember the model. The model is here. So this time, if we take variance on both sides, so we can calculate S naught for this model. So how about SH? Well, let's try to take covariances. With xt minus h on both sides. For h larger than 0. So what's the result? First of all, covariance of xt and xt minus h, that's sh by definition. So you have sh by definition on the right left hand side. Alpha can be ignored. So it's covariance of phi. Phi can be taken out. Covariance of xt minus 1 and xt minus h. Right? And then plus covariance of epsilon t and xt minus h. Now by what I've just talked about, this is 0 again, right? My h is larger than 0. T minus h, therefore, is a time point less than t, okay? So covariance of any current epsilons, any current white noise with our past process, they'll always be 0. So what you're left with is this. This, by definition, is covariance of the process x at different time points, right? What is the distance between these two time points? That's h minus 1. T minus h minus t minus 1, that is 1 minus h. Okay? And the ACVS should be symmetric around 0, obviously. So S1 minus h is SH minus 1. And that's it, really. So this is the result for h larger than 0. So how do we actually calculate the value of SH? Well, we can iterate this process numerous times. Let's iterate it once more. SH equals to phi SH minus 1. SH minus 1 equals to phi SH minus 2, right? So it's phi square SH minus 2. And so on and so forth until you have phi of h minus 1 S1 equals to phi of 2 to the power h times S0. Right? Iterate one more time in the end. 1 is still some lag larger than 0, so you can iterate it once more. And this is the end. You can't iterate it anymore because this is 0. The formula here is only valid when h is larger than 0. So what then? But you don't need to iterate it anymore because you know what S0 is from past calculation. So this is phi to the power h times sigma square divided by 1 minus phi square. And this is for h larger than 0, remember. And when h is 0, so this is still valid. When h is 0, you can see that this is sigma square over 1 minus phi square, which is in alignment with what we have calculated. So is h larger than or equal to 0? It's still okay. But how about less than 0? Well, we know that this is stationary. So for h less than 0, it should be equals to the corresponding positive counterpart. So, but SH should be symmetric around 0. So therefore, SH indeed will equals to phi to the power h. This time, it's not only h but absolute value of h times sigma square divided by 1 minus phi square. Why? When h is, let's say, minus 1, then this shouldn't be phi to the minus 1, but phi to the 1, right? S minus 1 is S1. S1 equals to phi sigma square divided by 1 minus phi square, okay? So it's phi to the absolute value of minus 1. When phi is minus 2, this is S minus 2 should be S2. S2 is phi square times this, okay? So make h becomes absolute value of h, indeed, will make the whole ACVS symmetric here. So indeed, h should be absolute value of h here. And this time, h indeed is true for all integers, okay? Including 0. Set is a set of integers. Okay, so I think I've done enough calculation. So I'll give you 5 minutes, okay? So after 5 minutes, please come back and we will talk about the rest of the materials. Oh.
Maybe I can put.
You write me an email,
Okay.
so I can answer you. Okay.
Otherwise, I can contact one of the managers from the program. They can also add you to Google.
Okay,
since I-
okay, go to show. But you can let me know. Okay.
Okay, perfect.
Send me
so
an
much.
email.
Perfect. I was going to. I have chronic back pain. I've had it since
Yeah.
I read my part. Whenever I went to the physiotherapist, they're like, well, most people who just do surgery, you're way too young for this. I'm like, right. Basically, I was trying to pick up a friend, and there was a pop in my spine. Like, that's it. It was written. It was fine for a little while. Like, it just has bad days. So I don't want to go out. I think it depends on the seats at this school are really shit. So like, whenever I'm sitting on those couches more than an hour, the next day I feel even the chairs there. Everything, like the only good chairs are the ones in
Okay, so let's get back to on track. So here I'm just going to show you a little bit of plot. Okay, so this is an AR1 model. So in R you can simulate. Let me show you this line of code a little bit clearer. So this is line of code. So if this arima.sim is the generic function which simulate AR or MA, or later on I'll introduce the ARMA model. So if you input, so AR coefficient equals to 0.5, this means it's an AR1 model. Okay. So if I input another constant, then there is an AR2 model and so on and so forth, okay? So with this AR2 model, so you can plot X. So it becomes an AR2 model. So it's plot of an AR2, okay? So doesn't really, not many notable feature if you are not comparing to a white noise. So let's compare to a white noise. So y equals to normal of the same 300, okay? So it produces a standard normal I dy noise, okay, of sample size equals to 300. So it's the same size as the x here, so I input n equals to 300, right? So if you plot the y as well, what do you get? So you get points here because I'm just producing 300 different random variables here observed, which may not be a time series. It at least not recognize it as a time series. Okay. When I simulate from arima.sim, so it will be recognized immediately as a time series. Okay. So if you want to recognize it as a time series, what you need to do is the simplest, okay, is plot.tx, okay. To give you the simplest solution. So it's a white noise, and this is something that I don't want. So let's plot x again, and then plot y again as a time series. Okay. So you can see that for the same sample size, perhaps they look a little bit different, right? So this is the AR2 model, and this is the white noise, okay? It's AR2 and white noise. So even by your naked eye, so you can see the difference. So the white noise has a little bit more fluctuations here compared to this AR2 model, okay? So you see for most of the parts, the number of fluctuations is less compared to the white noise, okay? And the reason, well, for this particular AR2 model, so basically it's looking like an average of the past values, okay? And the dominant thing here is the coefficient 0.5 here. So xt equals to 0.5, xt minus 1, okay? So most likely, xt will be similar in magnitude to xt minus 1, so it's just half of it. Of course, there's a minus 0.2, xt minus 2, okay? But it will be contaminated by the white noise as well, remember? So basically, xt, more likely than not, you can see even from this definition of the AR2 model, that xt at least will remains the same sign, okay? So if xt is positive, it equals to 0.5 xt minus 1. If xt minus 1 is positive, so xt will be 0.5 times something positive, so it's more likely than not it will stay positive, okay? And vice versa, okay? And therefore, well, if positive, the next value stays positive, that means it looks more smooth than fluctuation here. The fluctuation means sometimes it's positive, and then it goes negative immediately, and then vice versa, okay? So that's white noise, but not this AR2 model, okay? So look at this, if it's positive, if the next value stays positive, and then it still stays positive. And then finally it goes negative. And if it's negative, then it stays negative, and then negative, and then negative. Okay, so so I hope I makes my intuitive explanation a little bit clear. But mathematical reason, it goes back to frequency domain analysis, which I have removed from the course, okay? So but from the model of it, so I hope it's clear. If it's AR1 models, then the contrast is even larger. So this is the AR2 model. Now, if I make it just AR1, at the same time, let's make this coefficient 0.9. So what do you think it will happen? Even smoother, right? So xt equals to 0.9, xt minus 1. So xt most likely will be similar to xt minus 1. Of course it will be smooth. Okay, so there are fluctuations, but mostly it will stay positive when its previous value is positive. Of course, when epsilon t is large, then it's another story, but most likely it's not, right? So therefore, the whole trajectory of this AR1 model is quite smooth.
Excuse me.
Yeah.
If you are given a time series from recorded data, how do these, like the AR and the MA models, come and help with that? Like, can we like assume the data we're given is AR1? So
No, of course not. You need
well,
to
not assume, but like if it fulfills the same characteristics of an AR model, then you
Therefore, I'm teaching one characteristic at a time. Remember the MA model, I put a star on a property. Well, the ACF or the ACVS has a cutoff elect here, right? So if you plot the empirical ACF, and you can kind of see that, well, it had a certain cutoff point, let's say. It will not be exact cutoff, because it's empirical, but approximately it has a certain cutoff point, then you will suspect that it follows a MA model.
yeah, okay,
It's this kind of thing, okay?
yeah,
So basically, we were looking at the ACF, empirical ACF, as the tool, okay, for this kind of modeling, okay? And so I'm still
okay.
teaching that, okay? But look at another example first, okay? So this time it's still an AR1 model, but this time I put minus. So it's still a stationary AR1 model, but this time, what do you expect? Well, of course, even more fluctuation than a white noise does. Well, it's not surprising, xt is minus 0.9 xt minus 1. That means what most of the time xt will be minus of the xt minus 1. So it changes sign every time you change data, you change your time point. Okay? So for white noise, you don't know. Sometimes it changes, sometimes it doesn't. But for this AR1 model with negative coefficient, most likely it changed sign. Okay? So therefore, even more fluctuation than a white noise. Okay? So it depends on the sign of the coefficients, really. Okay? So for an MA model, it's similar, but let me not dwell on it. The important thing I want to talk about next is something I'm not going to write down, but you need to read it yourself, okay? So please read and be familiarized with the calculations in page 17, which is example 2.14, up to page 19, the end of example 2.14, okay? So this example 2.14 is basically telling you that, well, I give you an AR1 process. It certainly is actually not stationary. But why can I assume it's stationary? Okay, when I write something down, finding its ACVS, well, it's asymptotically stationary. All the AR process, basically all process you're talking about is, if you let the process run for a long time, then it will basically be approximately stationary, okay? So if a process runs from minus infinity, so it started at a time point which is very, very long time ago, then we can say it's okay, it's stationary. But if its starting point is here, you look, the starting point is minus m, okay, not minus infinity, well, it will not be stationary, even if phi is less than 1 in magnitude. But as you allow the time series to run for longer and longer time, it will approximately be stationary. That's example 2.14, okay? So you need to get a hang of how to do different kind of these calculations. What does it mean? And why the process is not stationary, but only asymptotically stationary, okay? I will give you exercise as well, okay? Don't worry, but you need to read example 2.14, okay? Now, let's go back to the .com. So with regard to the previous AR1 example, which is stationary, I will have another alternative calculation, okay? So alternatively, for this model, which is assumed stationary, how do we calculate the ACVS? So previously we take variance on both sides, so actually we can take covariance with epsilon t on both sides. So if we take covariance with epsilon t on both sides, the left hand side is covariance of xt and epsilon t. Right hand side, phi times covariance of xt minus 1 and epsilon t. This is 0, right? I've told you about it. And then plus the covariance of epsilon t and epsilon t. Well, what you're left with is just the last term, which is variance of epsilon t, which is sigma square. Okay? Sigma square. So how does it help with our calculation? Well, this time we really calculate it. So if we take covariance, now with xt on both sides, then the left hand side is S0, the right hand side is phi times covariance of xt minus 1 and xt, and then plus the covariance of epsilon t and xt. Now, none of these terms are 0, okay? So phi, by definition, covariance of xt minus 1 and xt, that's S1. And then the next term, so we have calculated in here, covariance of epsilon t and xt, we actually know the value is just sigma squared. And same as before, you know sh is phi of sh minus 1 for h larger than 1, meaning sh is phi to the power h times s0 for h larger than h larger than 1. In fact, it is it's valid for h equals to 1 as well. So this part is same as before. So this is done by taking covariance of xt minus h on both sides. Now how do we calculate the ACVS? Well, we have this equation and this equation. Well, basically it's just solving the equation, right? So firstly, S0 equals to phi times S1, and S1 equals to phi S0. Right? So we're using this equation here, this equation. And then S1 equals to phi times S0. So we come up with phi squared S0 plus sigma squared. This is indeed the equation that leads to S0 equals to sigma squared divided by 1 minus phi squared. Then all calculation follows, okay? It's the same as before. So different model, it requires you to maybe try to think about how to calculate the ACVS before you do anything, okay? Otherwise, the process may be more complicated than it should be. All right? Any questions? Okay. So I'll introduce another measure which is in parallel to the concept of ACF, okay? And the purpose is ACF had a cutoff for MA model at leg Q, right? So the measure I'm going to introduce will have a cutoff for the ACVS for AR model. So now you have empirical tool to look at data. So is it look like AR model or MA model? Okay. So what is this measure? So if you have done regression, so maybe you have done this, something called partial correlation. Here is the partial ACF, PACF. It's basically a parallel concept, okay? Partial correlation in regression means correlation between your response variable and the covariate, but taking out the effect of any other explanatory variables, right? That's partial correlation. So if you don't know what I'm talking about, it's fine, okay? I'm going to introduce it here anyway. For the partial ACF, it's similar. So let xt of course be stationary first of all, otherwise this concept will not hold. And define this. Define this partial ACF at leg J equal to the correlation. Now, very careful. I'm talking about correlation, not covariance here. CORR is correlation, okay? Correlation between xj minus 1, xj plus 1, sorry, and x1. Well, that's just correlation between xj plus 1 and x1. Well, that's just row 1. That's just row j, right? ACF at leg j. But if we subtract something, here we subtract some E hat here. What is this E hat, by the way? For x1, we subtract similar thing. E hat of x1 given all the random variables in between.
I'm sorry, what's the last sentence? It's like xj to x.
This one here?
Yeah, the one at the end, yeah.
Yeah, xj,
To
comma, x2, okay? So it's the random variables between x1 and xj plus 1. So between x1 and xj plus 1 is x2, x3, up to xj. Sorry about that, let me make it.
thank you.
Okay, so what I haven't finished the definition. What is E hat? So this E hat here, the E hat of y given factor of x. So I underscore means it is multivariate. So this is equals to alpha naught plus alpha 1 transpose times x minus the mean of x. Sounds complicated, right? So where alpha naught and alpha 1 are the solution, to this problem. Minimize alpha naught and alpha 1 over alpha naught and alpha 1, the mean square error function. So population mean square error. Okay. So what we are doing is basically at population level, we grasp y on this variable x. Yeah, it's basically a regression problem. But on population level, the criteria here is basically least square. But on population level, remember least square empirically is, well, sum of y minus the model estimator from the covariate xi. Here, I assume all of them are random variables, so we take expectation of the error squared. So this is doing least square estimation at the population level. So we're basically regressing y on x, finding the best coefficients for the constant and for the slope term, okay? Here is multivariate regression, so alpha 1 is actually multivariate, the same dimension as x, okay? And in our example here, so E hat of xj plus 1 given xj minus 1 back to x2, well, it means what? It means we are regressing xj plus 1 on the past value of the x. We are regressing xj plus 1 on xj plus minus 1 back to x2. Okay? And then the best regressed value is the E hat. So E hat is the best regressed value for y. So it's basically the best value of y as linearly explained by x. Okay, so that's what linear regression is means. Okay. So the best linear value explained by the past value x2 up to xj for xj plus 1 is this E hat xj plus 1 given these past values. The same for E hat x1, okay? So this time is basically, well, it's a kind of a reverse, right? Time reverse regression. We're regressing x1 on future values. Regressing x1 on x2 up to xj. So the best linearly explained x1 by its future value x2 up to xj, that's this E hat x1 given xj minus 1 back to x2. So I know it's a little bit complicated, the concept, okay? Therefore I go a little bit slower, okay? The meaning is important. The meaning is important. And this appear on your week 2 exercise as well, okay? So therefore I need to talk about how to do this. I'll talk about this in the seminar, but I don't know if Kai-Sin has talked about that, so I need to talk about this. A little bit of example very quickly. So if epsilon 3, let's say, is uncorrelated with x2, now for an AR model, indeed epsilon 3 is uncorrelated with x2, right? I've talked about that. Then the best linear estimation of epsilon 3 by x2 is what? It should be 0. If it's uncorrelated, then there's no linear relation. So this E hat should give you 0. Let's check it out if it is 0 or not. So E hat equals to, okay, alpha naught by definition, alpha naught plus alpha 1. This time x2 is just one dimensional, so alpha 1 is one dimensional, so it's alpha 1 x1 x2 minus the mean mu. This mean mu is just expectation of x2. Right? Where your alpha naught, alpha 1 are solution to the minimization problem. Epsilon 3 minus alpha naught minus alpha 1 x2 minus mu squared. Let's expand this squared. And hopefully you can see this really quickly. So what is this? This is, first of all, expectation of all these squares. So expectation of epsilon 3 squared plus alpha naught squared plus alpha 1 squared times the expected value of x2 minus mu all squared, which is variance of x2. Is it the end? Well, of course, there are cross terms. You need to talk about the cross terms. But the cross terms with alpha naught, they are all 0. Expectation of epsilon 3 is 0, so cross term is 0. Expectation of alpha 1 x2 minus mu, of course, is 0. So cross term with alpha naught, taking expectation is still 0. Okay? There are 3 cross terms. One is with epsilon 3 and alpha naught. One is alpha naught and alpha 1 x2 minus mu. The other cross term is epsilon 3 and alpha 1 x2 minus mu. Is this cross term 0? Well, x2 and epsilon 3 are uncorrelated. I assume it here. Then this first term and third term, of course, still have expectation equals to 0. Okay? So all cross terms are actually 0. Okay? So indeed, this will be the value of the expected value of this squared. Now, how to minimize this? It's completely obvious now. How to minimize this? Alpha naught equals to alpha 1 equals to 0. You're just minimizing sum of squares. Putting alpha naught and alpha 1 0, so this will be minimized. Nothing you can do about expectation of epsilon 3 squared. So therefore, your E hat of epsilon 3 given x2 for epsilon 3 and correlated with x2, this is 0. As it should be. As it should be. Through calculation, this is 0. And from the meaning, epsilon 3 is uncorrelated with x2. The meaning of E hat is, again, the best linear estimator of epsilon 3 given x2 here. And the best linear estimator, of course, is 0, okay? Because they are actually uncorrelated, okay? All right. So I hope this will clear up a little bit, but I need to maybe give you another example so that you can do the exercise at least. And I also need to clear this up about a little bit more detail. So let's give a little bit more complicated example. So let's go back to this AR1, okay? So it's W is a white noise with mean 0 and variance sigma square. Now, let's assume again xt is stationary. So what is pi 2 then? Pi 2 is the correlation between x3 minus E hat of x3 given x2 and x1 minus E hat of x1 given x2, right? That's by definition. The random variable between x1 and x3, that's only x2, so it's given x2. Now, we need to look at E hat of x3 given x2. It equals to E hat of alpha plus phi of x2 plus epsilon 3. That's expansion of x3 using the AR1 model. Given x2, okay. And this equals to, well, E hat of something added together will be the sum of the E hats of those things, okay? So it's basically this plus E hat of epsilon 3 given x2. So you can prove this property, but I hope this shouldn't be too difficult to see. So E hat has a linear operator property. So E hat of x plus y given b is E hat of x given b plus E hat of y given b. And this, we have proved that is 0 because epsilon 3 indeed is uncorrelated with x2. And what you're left with, this is alpha plus phi x2. You can verify the calculation yourself, or think about the meaning of E hat. What is the best linear estimated value of alpha plus phi x2 using x2? Of course, it's alpha plus phi x2 itself. Okay, it's a function of x2 already. It's a linear function of x2 already. Okay, so there you go. It's itself. So therefore, your pi 2 will be the correlation between x3 minus alpha minus phi x2, and then x1 minus e hat of x1 given x2. Well, you can calculate this, but I'm not going to calculate this here because I don't need to. Ultimately, this is what? This is correlation between epsilon 3. That's what's left with here in this subtraction. x3 minus alpha minus phi x2. Epsilon 3 is the result. And then x1 minus e hat of x1 given x2. And I can immediately say, okay, this has to be 0, right? Why is that? Well, epsilon 3 and x1, of course, correlation between them is 0. But what is e hat of x1 given x2? Well, you know it, at least by definition, is some coefficient times x2, whatever the coefficient is. That's by definition. So x1 minus e hat x1 given x2 is a linear combination of x1 and x2. And correlation between epsilon 3 with something of a linear combination of paths x, x1 and x2, of course is 0. Okay? So this is 0. The important thing is this is 0, okay? In fact, pi j is 0 for j larger than or equal to 2 for this stationary AR1 model. And in fact, so this ARP model always has a PACF cutoff at lag P. Cutoff at lag P means what? Means beyond P, the PACF is 0. So for this AR1 model, beyond lag 1, that means starting from lag 2 onwards, all the PACF are 0. So as proved here. So you can prove for pi j. For pi j, j larger than 2 is basically the same calculation really. Okay, try to do that.
And that fact's always true.
Sorry?
The AR, that ARP has a PACF cutoff, that's always true?
Yes.
It is, okay.
Yeah. Of course, it needs to be stationary, okay? We're talking about stationary ARP model. But what is pi 1? Pi 1 is phi, okay? For this AR1 model. So I really left it as exercise if I haven't, okay? So try to do this, well, follow the definition. So you should be able to arrive at phi 1 equals to phi. So you have two empirical tools, so PACF and ACF. So without, so let me go to the lecture notes, okay? So let's copy it later on if you haven't done this. So we can now look at the empirical PACF and ACF. Well, hey, I haven't talked about how to calculate empirical ACF, ACVS, or PACF, okay? So let's assume we know the empirical version for a moment, so we'll maybe touch this in the next lecture. So with this empirical ACF and PACF, so you should be able to find the order of models if they are really AR or MA model, okay? So here, let's suppose let's consider the previous example, the AR2 model. 0.5 minus 0.2, okay, so this is X. So X follows an AR2 model, the sample size is 300. Well, Well, if we look at is ACF and PACF, what should we see? Okay. Sorry. No. Not ACF2. So this is the ACF. Now this is an AR2 model. For AR model, the ACF should really be exponentially decreasing, for a stationary model at least. So, well, this blue dotted line, I will explain it maybe hopefully next lecture, but it's kind of a confidence interval, okay? Because it's empirical, so even if population value is 0, so the empirical value is not 0 for the ACF. But therefore, so there's a confidence interval. So for the first one, of course, equals to 1, ACF at lag 1 equals to 1. ACF at lag 2, at lag 0 equals to 1. And lag 1, of course, is not 0. And then starting from lag 2, well, it goes into the confidence interval. So it's kind of look like 0. But, and then the lag 3, it stick out from the confidence interval a bit. But most of the other terms, so they goes back into the confidence interval. So maybe we know that this is an AL2 model, but it looks like there's a cutoff at lag 1 actually. It looks like an MA1 model. Okay. So let's produce another simulation path. Now this time you see there's something more obvious sticks out at lag 3 and 4. Okay, but not beyond. Okay, so it decreased very significantly after the first few lags. Okay, but the population ACF, so you have seen for AR1 model, so it's exponentially decreasing. In fact, for any stationary AR model, the ACF also is exponentially decreasing in magnitude. Okay. When there's negative coefficient, it somehow could be that there's a wave-like property, but magnitude is decreasing. Okay. So you can say, okay, it looks like an MA4 model. Well, with sample size equals to 300 only. Well, practically, perhaps you really can model it like MA4. Although I simulated using an AR2, right? In all practical terms, so it looks like MA4, okay? So it looks like MA model with that kind of sample size, okay? So if we increase the sample size equals to 3,000 this time, so what will we see? Similar things happens, okay? So if we have a larger sample size, confidence interval, well, will be actually narrower, okay? So it's more accurate estimation. Anyway, so how about PACF? So if we load the ASTSA library, there's a function called ACF2. ACF2. ACF2 means you plot the ACF as well as the PACF and juxtapose them side by side for comparison. Okay, there's grid value as well, so it's actually better. ACF2, okay, from the ASTSA library. It's also, I think, in the lecture note I used that. So now you look at the PACF. Well, the PACF, the cutoff is more obvious for the PACF. And what is the cutoff lag here? After lag 2, it goes really into 0. Okay, so let's look back at the sample size equals to 300 this time. Similar thing, okay? So it doesn't plot leg 0. Leg 0 is uninteresting. It's always 1, okay? So it's basically making it difficult to look at other values, okay? So we start from leg 1 stick out, and then the other legs, well, it could be MA3 kind of thing, okay? In all practical terms, again, it could be MA3. But from the PACF, the cutoff is very clear, so it's leg 1, leg 2, and then, well, nothing. Maybe after leg, I don't know, leg 6, 7, 8, maybe leg 8, there's something. Well, remember, it's 95% confidence interval here, this blue dotted line, so there could be something that sticks out that is completely by chance, okay? You're looking at data here. Okay?
Okay, so everything inside the blue dotted lines
Yep.
is like explainable, and then everything that sticks
It-
out of the lines is.
It's basically like a 95% confidence interval for the ACF or PACF here. Okay, so I will explain it a little bit more clear in the next lecture. But for now, looking at it like confidence interval. So if it's inside the confidence interval, that means it's basically you can assume that it's 0. Okay, it's basically okay. I perform a test. If it's 0 or not, well, the p-value then will be larger than 5%. Then it's you can assume it's 0. Okay, this kind of thing. Okay. So leg 1, leg 2, okay, outside this blue dotted line, okay, so that's significantly different from 0, but all others, well, they are within the dotted line, okay. And this aligns with a population value, okay. In population value for this AR2 model, leg 2 onwards, the PACF will be 0, but not leg 2 itself, okay. So cut off the leg 2. All right, so I hope I demonstrated it quite clearly. Okay, so that's the PACF, and for I don't have enough time to give you other. To introduce the ARBA model, okay, but I'll leave it in the next lecture, okay. So please come back in the next lecture. So we'll continue with some other more complicated models, and how do we actually look at stationarity itself? How to see very quickly if a model is stationary or not, okay. So this relates to the AR portion of the model, okay? So next time we'll see that, okay? So I'll see you guys next week. So for those who are staying for the seminar, so I'll see you in 05, okay?
You click on that button, and then you just add. I can get back.
I could say that.
And then 4 o'clock on Thursdays.
What's the Thursday times? What are the Thursday times? What's the Thursday time?
45. What do you have?
Dissertation. So I'm contributing to maths as a subject. So it doesn't matter.
But then we're going to mark this absent.
Yeah, because it automatically updates it.
Yeah, but it doesn't. But then yesterday I wasn't there, so I don't know. Sorry. I just wanted to let you know, I just switched seminar groups to the one on Thursday.
Oh,
So
okay.
then I come in on Thursday for next week, but today I'm just gonna stay.
Okay, okay. Yeah, no problem.
So what else do you have planned with your drawing that thing next week?
I might actually go outside. I'm gonna.
Can you come into the thing with Jacob?
I have no idea. I just messaged Archie because Archie was like, I'm doing this, this, and this, and I'm like, oh, I'm down.
Is it like,
He's like my social attaché. He just tells me what to do and when to get.
this?
Oh, I haven't been sent the details at
Oh,
all.
how did you-
Just that something was happening. I'm like, oh, I might be able to make it.
So what made you change your mind?
Yeah,
Really?
I mean, partially kind of.
That made me change my mind tonight?
What do you mean, send it?
That's kind of boring.
So please take the attendance, okay? So write down this information, okay?
I do. I am organized.
Sorry. Really close. So when did Thomas go?
No.
He just left, right?
He's like avoiding like way too many courses.
Is it auditing before?
I think
What
so.
is in it?
No, I think he's auditing it. Which makes no sense to me.
Why?
I get the idea of wanting to audit, it's like, oh, you want to experience and learn other things, but at the expense of what you're currently